Rusting cargo ships stranded in an endless desert. That's the verdict. That's what remains when you drain the fourth largest lake on Earth in half a century. We're looking at the Aral Sea in Central Asia, a water body that once covered roughly 68,000 square kilometers in the early 1960s and sustained millions of people across one of the most unforgiving landscapes on the planet. This wasn't a natural disaster. This wasn't climate change alone. This was an engineering decision, a choice to prioritize cotton over water. And the execution was so precise that by the 1980s, the sea had already begun to die. The Aral Sea sat at the intersection of Kazakhstan and Uzbekistan, fed by two massive rivers, the Amu Darya flowing from the south and the Sir Darya descending from the northeast. Together, they delivered enough fresh water to sustain a lake so large it regulated the climate of the entire region. It was an oasis in the desert, a place where fishing boats hauled in tens of thousands of tons of fish every year, where delta wetlands stretched for hundreds of kilometers, where the sheer volume of water softened the brutal extremes of a continental climate. The sea wasn't static. It had fluctuated for centuries in response to droughts and floods, but it always recovered because the rivers always returned. That baseline held until the early 1960s, when Soviet planners decided the water was worth more in cotton fields than in the lake. The system that kept the Aral Sea alive was brutally simple. Two rivers delivered the input. The lake absorbed that water, regulated salinity through natural overflow and evaporation, and sustained an ecosystem that depended on continuous replenishment. The output was a stable, relatively fresh body of water covering tens of thousands of square kilometers. The degradation began the moment that input was severed. In 1962, the Karakum Canal opened, diverting up to 45% of the Amu Darya's flow south into Turkmenistan to irrigate cotton and wheat. The Sir Darya was similarly tapped. By the mid-1960s, the inflow to the Aral Sea had been cut nearly in half. The lake began to shrink, and once that process started, every mechanism that had sustained it began to fail. The first thing to understand is that the Aral Sea was a freshwater engine. It wasn't an ocean. It was a terminal lake, meaning no rivers flowed out of it. Water left only through evaporation, and the rivers constantly replaced what was lost, keeping salinity low, around 10 grams per liter in 1960. That level of freshness made it possible to sustain fish species that thrived in brackish but not hyper-saline water. The fishing industry that depended on this was enormous. At its peak in the late 1950s, the Aral Sea produced roughly 40,000 tons of fish annually, supporting tens of thousands of jobs in processing plants and port towns like Aralsk and Muinak. The mechanism here was straightforward. Fresh water flowed in, fish populations remained viable, boats went out, and towns prospered. When the inflow dropped, salinity began to climb. By the early 1970s, it had doubled. By the 1980s, it exceeded 100 grams per liter in some areas, 3 times saltier than typical seawater. Fish stocks collapsed. The commercial fishing industry died by the late 1980s. The reality check is those cargo ships. They sit in the sand today, miles from any water, because the shoreline retreated so fast that entire ports were abandoned before the boats could be moved. The second mechanism was climate regulation. The Aral Sea was massive enough to function as a thermal buffer. Water has a high heat capacity, meaning it absorbs and releases energy slowly. In summer, the lake absorbed heat, cooling the surrounding air. In winter, it released stored warmth, moderating the cold. This created milder seasonal transitions across the entire basin. Winters were less severe, summers were less scorching, and the growing season was longer. The degradation of this system was immediate. As the lake shrank, its thermal mass dropped. The land that had been covered by water became exposed desert, which heats and cools rapidly. Winters grew colder by an average of 3 degrees Celsius. Summers grew hotter. The growing season shortened. Dust storms, which had been rare, became routine. The visible proof is in the sky. On bad days, thick clouds of dust block the sun completely, and satellite images show plumes stretching hundreds of kilometers downwind. The lake that once softened the climate had been replaced by a heat sink that amplified every extreme. The third mechanism was the delta wetlands. The Amu Darya and Seer Darya didn't simply dump water into the lake. They created vast marshes and floodplains at their mouths, ecosystems that supported reeds, grasses, fish spawning grounds, and migratory birds. These wetlands existed because the rivers delivered enough water to sustain them, even in a desert. When the diversions began, the deltas dried up. The Amu Darya Delta, once covering thousands of square kilometers, became cracked earth. Vegetation died. Species that depended on the marshes disappeared. The reality check is visible from space. Satellite images from the 1960s show lush green deltas. Images from the 2000s show barren, fractured soil. The wetlands didn't degrade slowly. They collapsed within 2 decades because the mechanism that sustained them, continuous river inflow, was cut off. But the degradation didn't stop with water loss. There was a secondary accelerator, and it made everything worse. The newly exposed seabed wasn't clean sand. It was laced with agricultural runoff, decades of pesticides, fertilizers, and salts that had washed into the lake from the same cotton fields that had stolen its water. As the lake shrank, this toxic sediment dried and became dust. Winds picked it up and carried it across the region. The dust storms that now plague the area aren't just sand. They're chemical storms, delivering measurable concentrations of DDT, heavy metals, and other toxins into the air, the soil, and the lungs of everyone living downwind. The mechanism here is simple but vicious. The irrigation that drained the sea also poisoned the seabed. The shrinking lake exposed that poison. The desert climate weaponized it. The result is a feedback loop where the same system that destroyed the water now actively harms the people who remain. The cascade of consequences followed a brutal logic. First, the freshwater oasis became a hyper-saline desert. Second, the fishing industry collapsed, and prosperous port towns like Muinak became ghost towns. Third, the regional climate destabilized, making agriculture harder even in the areas that had received the diverted water. Fourth, public health deteriorated. Rates of respiratory disease, anemia, and kidney problems surged among the adult population in former coastal areas, driven by toxic dust exposure and contaminated drinking water. Fifth, the exposed seabed became the Aral Sea Desert, a new desert covering more than 50,000 square kilometers that didn't exist before 1960. Each of these consequences wasn't a random side effect. Each was a direct, predictable result of severing the river inflow. The trajectory isn't uniform. The Aral Sea split into 2 main basins as it shrank. The northern basin, fed by the Seer Darya, was partially saved. In 2005, Kazakhstan completed the Aral Dam, a low dike that prevented water from draining south into the larger, deeper basin. The northern sea stabilized at roughly 10% of the original total volume. Water levels rose slightly, salinity dropped, and some fish species returned. It's not a recovery, but it's a halt. The southern basin, fed by the Amu Darya, continues to shrink. Uzbekistan still diverts most of the Amu Darya for irrigation, and without inflow, the southern sea is evaporating. Satellite measurements show it fragmenting into isolated pools, some of which disappear entirely during dry years. The trajectory here is conditional. If diversions continue at current levels, the southern basin won't stabilize. If upstream countries increase water use, which climate models suggest they will as temperatures rise and glaciers shrink, the remaining pools will dry completely. Tracking this collapse requires watching specific signals. First, salinity levels. Rising salinity is a direct measure of how much the input has been cut. When salinity exceeds 100 grams per liter, almost nothing survives. Second, surface area. Satellite measurements provide the most unarguable proof of loss. The Aral Sea covered roughly 68,000 square kilometers in 1960. By 2014, it had shrunk to less than 10% of that. Third, upstream snowpack and glacial melt. The rivers that fed the Aral Sea originate in high mountains. Climate projections indicate that snowpack is declining and glaciers are retreating, which means even if diversions stopped tomorrow, the rivers would deliver less water than they did in the past. Fourth, health statistics. Respiratory disease rates, anemia, and kidney problems in towns like Nukus and Muinak are canaries in the coal mine. They reveal the human cost of toxic dust exposure. Fifth, dust storm frequency. The more seabed that's exposed, the more material is available for the wind to lift. Increasing storm frequency means the desert is still growing. The Aral Sea was killed by an engineering decision. Soviet planners in the 1950s and 60s believed they could turn Central Asia into a cotton empire by diverting the Amu Darya and Sir Darya. They succeeded in growing cotton. Uzbekistan became one of the world's largest exporters. But the cost was the destruction of a lake that had regulated the climate, sustained an industry, and provided water security for millions of people. The planners knew the sea would shrink. Internal documents from the period show they considered it an acceptable trade-off. What they didn't anticipate, or chose to ignore, was the speed of the collapse, the toxicity of the exposed seabed, and the long-term climate impacts. The Aral Sea didn't die because of a drought. It died because the system that sustained it was deliberately dismantled. And once the inflow stopped, every mechanism that depended on it failed in sequence. The reframe is this. The Aral Sea wasn't fragile. It had survived droughts, floods, and climate shifts for thousands of years. It died because a single input, river inflow, was cut below the threshold required to sustain the system. The lesson isn't about respecting nature. It's about understanding thresholds. Every system has a minimum input required to maintain its function. Cross that threshold, and the system doesn't degrade slowly. It collapses. And once it collapses, restoring it is vastly harder than preventing the collapse in the first place. The northern Aral Sea shows that partial recovery is possible with targeted intervention. The southern basin shows what happens when that intervention never comes. Thanks for watching. If this breakdown made sense, hit like and subscribe. Drop a comment with the next water body you want analyzed. Should we look at a dying river or a disappearing lake next?